In one of the previous tutorials, I worked some problems from Lab 4.1.1 to illustrate how we can use the standard form of propositions on the square of opposition using quantifiers as a clue to guide us as we formalize propositions that roughly correspond to one of the four traditional types. In this tutorial, I'm going to start with a problem from that same lab exercise, 4.1.1. This is problem number 9. Not all animals are primates, and I am going to show you a very important relationship between the universal and the existential quantifiers. It actually turns out to be quite similar to the relationship we have on the square of opposition. So if we formalize this particular proposition, not all animals are primates, what we have is not. So it's not the case that all animals are primates, right? Where the not applies to all of this. So that is an A proposition, and so if we say it's not the case that all A is P, then what we are saying is that it is the case, see the corresponding, the contradictory, right? The corresponding O, it is the case that some animals are not primates. Okay? So, the negation of one of the propositions on the square of opposition leads us to conclude the contradictory. So, it's not the case that all A is P, leads us to assert that some A are not P. So, in other words, the negation of an A leads to the assertion of an O. That makes pretty good sense from the intuitive aspect of this, but let's see how things fare when we do quantifiers. So let's start with what's inside the scope of this negation here. All animals are primates. So taking a clue from our standard form, we're going to say for any x, if x is an animal, then x is a primate. So this is what the proposition looks like, formalized. That's inside the parenthesis there. So what we want to do then is we want to just negate this whole thing. So it's not the case that all animals are primates. More formally, it's not the case that for any x, if x is an animal, then x is a primate. Now, what we ought to get with this negation, we ought to get this particular, right here, this particular, in other words, the O. We ought to get something like that. So what's that? There is an x such that x is an animal and not a primate. Okay? So somehow or other, these two need to turn out to be logically equivalent. How do we show that they are logically equivalent? Well, that's where a technique called the quantifier exchange rule comes into play. Okay? So if we have a negation side that has within its scope a quantifier, so here we go. So it's not the case that for any x, A of x implies P of x, then we can invoke this quantifier exchange rule. And here's how it works. The negation sign moves inside the scope of the quantifier, and we exchange the quantifier for whatever the opposite quantifier is. So since we started with a universal quantifier, we're going to switch to the existential quantifier. The negation sign moves inside the scope of the quantifier, and now the negation sign applies to everything inside, just like that. Everything inside the scope of the quantifier, the old quantifier. All right? Does that make sense? Yes. Let's look at it again. So here's the quantifier. The negation applies to the quantifier. It's a universal quantifier. and then the quantifier applies to the expression. So what happens with the quantifier exchange rule is the negation sign moves inside the scope of the quantifier. We change to the opposite quantifier, so we go from universal to particular, and we end up with there is an X such that it's not the case that if X is an animal, then X is a primate. Now, here, our normal propositional calculus axioms could kick in, and we could try to find a simpler expression for this negation. And so what might that be? Well, let's use the axiom that allows us to rewrite an implication as something else. Like, what about this? It's not the case that A of X or P of X. So this comes from our axiom, P implies Q, is logically equivalent to not P or Q. So this is one of our equivalence rules. It's an axiom, so we should be able to write logically equivalent expressions in place of each other. This is why they're sometimes called substitution rules. So what we did is we took an implication, just like that, it's the schema, and we rewrote it as a disjunction, in other words, with this schema. Now, the rest of the expression needs to go in place. So we have our existential quantifier, the negation sign. All right, now, what can we do with this whole expression? This expression corresponds to something like this. And so what if we look at our axioms and we see that if we invoke De Morgan, we can actually rewrite the negation of a disjunction as the conjunction of two negations. Now, on the front end here of this disjunction, we have an expression, and we need to negate that expression. It doesn't matter that it has a negation sign already there. We just need to negate whatever it is. So see, the form looks something like this, right? And then when we're applying De Morgan to this disjunction, we need to end up with the conjunction of not only this negation, but the other side negated as well. And so that gives us, it's not the case that not P and not Q. So we could do exactly the same thing here to this expression, just keeping everything intact, meaning we've got our existential quantifier. We can write, it's not the case that not A of X or not P of X. So notice this expression follows exactly the schema of this because this and this have the same schema. Now if we apply double negation, we can get rid of these two negations together, and what do we end up with? We end up with there is an X such that A of X and, sorry, I wrote or there, it should have been and not P of X. And that is exactly the expression that we predicted we should get by looking at the square of opposition. So on the square of opposition, the negation of an A should be logically equivalent to O by contradiction. In other words, if not A is true, then the O must be true. They're logically equivalent. And what we've done using the quantifier exchange rule plus the usual axioms of our system of propositional calculus is we've been able to show that if we start with the negation of a universally quantified proposition, through a series of steps, we can demonstrate that it is logically equivalent to the form that would correspond to O. Or to make a long story short, it's not the case that for any X, A of X implies P of X is logically equivalent to, there is at least one X such that A of X, but not P of X.